Greetings, ladies and gentlemen. My name is Ron van Schalkwyk from the University of Stellenbosch. My colleagues Dr. Hubert van Eerden and Ms. Julia Lloyd and myself form part of a macro-logistics research group that specializes in sustainable freight transport systems, and currently we are looking into answering the question of, can hydrogen be a clean fuel source for sustainable road freight transport in South Africa? On the agenda today are 11 main points to cover. Firstly, some background on hydrogen, the different types of hydrogen production, the overall process efficiency, the future of hydrogen for South Africa, the scenarios for model implementation, the hydrogen energy demand in the freight truck sector, the subsequent impact on carbon dioxide emissions, the renewable energy required to produce hydrogen, the hydrogen production infrastructure costs, the hydrogen distribution infrastructure costs, and finally ending with conclusions and future areas of focus. Let's begin with some basic hydrogen background from an energy perspective. Hydrogen is a carbon-free energy carrier. It is 3 times more energy dense by weight than conventional hydrocarbons, but 4 times less energy dense by volume. It needs to be compressed to 790 times atmospheric pressure to have an energy usable volumetric density, which is an energy intensive exercise. It can be liquefied at negative 283 degrees Celsius at atmospheric pressure, which is an even greater energy intensive exercise. But most importantly, the production of hydrogen utilizes energy carriers as feedstocks. Among the different types of hydrogen production methods are green hydrogen, which is produced by electrolysis using electricity from renewable sources; black hydrogen, which is extracted from natural gas using steam methane reforming; turquoise hydrogen, which is produced by the thermal splitting of methane; yellow hydrogen, which is produced by electrolysis using grid electricity; and brown hydrogen, which is produced by gasification using coal. For zero carbon emissions, the focus will therefore be on green hydrogen. The process begins with a slight energy loss from grid transmission to yield 100 kilowatt hours of renewable AC electricity. It is converted into DC electricity by a 90% efficient rectifier before entering the 68% efficient alkali electrolyzer cell, giving 61 kilowatt hours of energy in the form of hydrogen. The hydrogen is then compressed to a usable density, losing 13% of energy to heat, resulting in 53 kilowatt hours of energy in the form of compressed hydrogen for distribution. The compressed hydrogen enters a 60% efficient fuel cell and leaves as 32 kilowatt hours of battery storable DC electricity. A 90% efficient inverter then converts the DC electricity from the battery to AC electricity, which powers the 95% efficient AC motors, giving you 27 kilowatt hours at the wheel for a 27% overall efficiency. The future of hydrogen for South African road freight hinges on 3 major sections: electrolysis efficiencies, hydrogen fuel cell advancements, and curtailing distribution losses. Starting with electrolysis, transitioning from an alkali electrolyzer cell to a solid oxide electrolyzer cell increases the 68% electrolysis efficiency to 84%. Solid oxide electrolyzers are currently at a technology readiness level of 6, awaiting commercial availability, but can be expected to be implemented by 2045 to increase the overall efficiency from 27% to 34%. Next, hydrogen fuel cell advancements can be made to approach a 90% theoretical efficiency. If such improvements are to be made, we can expect the overall efficiency to increase from 27% to 41%. When combining improved electrolyzer efficiencies with advanced hydrogen fuel cell technology, an overall future efficiency of 51% can be expected. Finally, distribution losses are to be considered, as 10 to 40% of energy can be lost in the transportation of hydrogen, which can decrease the future overall efficiency from 51% to 30 to 46%. These losses can be curtailed by comparing central and distributed production facilities. Central production facilities decrease production costs due to increased quantity, but increase distribution costs due to increased transport distances. Distributed production facilities are likely to increase production costs due to decreased quantity, but decrease distribution costs due to decreased transport distances. Freight hydrogen fuel cell vehicles have the potential to cover a range of 1,600 kilometers. The major corridors considered to cover the greatest freight volume concentration are 550 kilometers from Gauteng to Durban and 1,500 kilometers from Gauteng to Cape Town. The following two model scenarios are based on freight demand estimations imposed into the South African Times model. The South African Times model generates different scenarios of hydrogen applications, which are aggregated to determine the South African demand for hydrogen approaching 2045. The model covers hydrogen applications in light, medium, and heavy commercial vehicles. Scenario 1 estimates that hydrogen replaces 5% of freight truck diesel by 2030 and 25% by 2045. Scenario 2, on the other hand, estimates that hydrogen replaces 20% of freight truck diesel by 2030 and all of it by 2045. Looking at the freight truck energy demand, it is estimated that the total energy required by freight trucks would be 192 petajoules by 2045. This is based off of a freight demand model, which estimated that a total of 7.44 billion liters of diesel was used by freight trucks in 2019. Scenario 1 would leave 155 petajoules remaining to be covered by diesel in 2045. Conversely, Scenario 2 estimated that hydrogen meets the total freight truck energy demand by 2045. Looking at the subsequent impact that these scenarios have on the carbon dioxide emissions from the freight truck sector, the control scenario provides a reference and assumes that no road freight hydrogen technology is implemented. Scenario 1 leaves 11 megatons of carbon dioxide remaining by 2045, while Scenario 2 estimates a carbon zero freight truck sector by 2045. Now, to determine the renewable energy requirements necessary to realize either scenario, a 1-to-1 ratio of onshore wind energy to solar PV energy production is assumed. The wind farms are expected to operate on an annual capacity of 35%, while the solar PV farms are expected to operate at 25%. Implementing these conditions allow for the following renewable energy production with the current wind and solar PV capacity as a reference. Assuming all current onshore wind and solar PV energy production is shifted towards hydrogen production to meet this scenario demands, the current wind energy capacity should increase threefold for Scenario 1 and 12-fold for Scenario 2 by 2045. Similarly, the current solar PV energy capacity should increase 5-fold for Scenario 1 and 19-fold for Scenario 2 by 2045. Including the current onshore wind farm area, the total onshore wind farm area required to achieve its capacity increase should be 1,720 square kilometers for Scenario 1 and 6,440 square kilometers for Scenario 2 by 2045. Similarly, the total solar PV area required to achieve its capacity increase should be 290 square kilometers for Scenario 1 and 1,090 square kilometers for Scenario 2. For context, this would mean that roughly a fifth of the Netherlands, or about 2/5 of Gauteng, should be covered in wind and solar farms to meet the renewable energy requirements for a carbon zero freight truck sector by 2045. Looking at the associated infrastructure costs to meet both the renewable energy requirements and electrolyzer production requirements, Scenario 1 requires capex expenditure of 49 billion rand by 2030 and 432 billion rand by 2045. Similarly, Scenario 2 requires 509 billion rand by 2030 and 1,909 billion rand by 2045. Therefore, the infrastructure cost required to achieve the renewable energy capacity increases add up to 349 rand per kilogram of hydrogen to be produced. Next, electrolysis infrastructure are costed according to a capex per kilowatt basis for alkali electrolyzer cells by 2030 and solid oxide electrolyzer cells by 2045. Therefore, the infrastructure cost required to produce the associated hydrogen adds up to an average 100 rand per kilogram of hydrogen produced from the electrolysis infrastructure, assuming the electrolyzers operate on an annual capacity of 40%. In total, the infrastructure cost required to produce the total amount of hydrogen required adds up to an average 419 rand per kilogram of hydrogen to be produced. Interestingly, the CSIR estimated that green hydrogen is estimated to cost around 50 rand per kilogram. Currently, diesel would cost around 50 rand to get the equivalent energy output in the form of 3.2 liters of diesel per kilogram of hydrogen. Therefore, for equal transport effort, a hydrogen solution would cost roughly the same as a diesel solution in 2021. Finally, the distribution infrastructure cost required to transport the hydrogen can be calculated according to a per energy basis estimated by the model. Scenario 1 requires 0.8 megatons of hydrogen to be transported compared to Scenario 2's 3.1 megatons by 2045. As such, Scenario 1 requires capital expenditure of 34 billion rand by 2030 and 136 billion rand by 2045. Similarly, Scenario 2 requires 135 billion rand by 2030 and 508 billion rand by 2045. Therefore, the infrastructure cost required to distribute the hydrogen adds up to 166 rand per kilogram of hydrogen to be transported. For reference, the diesel equivalent distribution infrastructure cost per kilogram of hydrogen transported adds up to 4 rand per kilogram of hydrogen to be transported. The significant difference is due to the low infrastructure cost per distributed diesel energy estimated by the model, which can mostly be attributed to hydrogen's comparatively low energy density by volume, resulting in high distribution energy losses. Ultimately, you can implement infrastructure to distribute 3 times the mass of diesel for 1/40th the cost of the energy equivalent in hydrogen infrastructure. To conclude, the overall process efficiency can increase from 27% to 34% by 2045 and can potentially get to 51% thereafter. The land area required for the renewable energy infrastructure is significant. However, South Africa has extensive land area available for applications of onshore wind and solar PV resources. The land area to be covered by renewable energy infrastructure is less than 1% of the South African land area available. Land areas that cover less than 2.5% of the total land area available are not considered significant enough to disturb the remaining areas. The future cost of hydrogen is estimated to roughly equal the current cost of diesel to provide the equivalent energy. However, hydrogen distribution infrastructure is 40 times more expensive than its energy equivalent in diesel. Ultimately, a fair argument can be made for hydrogen utilization in the battle for a carbon zero freight truck sector, both in its future efficacy and associated costs. Regardless of whether or not hydrogen is used, stored electricity should be used for vehicle propulsion, as this would be a better energy use than coal supplementation. It is recommended to get solid oxide electrolyzer cells to commercial availability as soon as possible. Next, the hydrogen fuel cell should be optimized, potentially through the improvement of current platinum catalysts, of which South Africa has platinum group metal reserves. Next, the central and distributed production facilities should be compared to minimize distribution energy losses, along with determining the optimal placement of these facilities on major corridors. Finally, and most excitingly, Hydrogen storage mediums, such as liquid organic hydrogen carriers, can be utilized to capture produced hydrogen for decreased distribution energy costs. The hydrogen can then be extracted and utilized as necessary to offset the potential waste of surplus renewable energy, increasing both the efficacy and robustness of future hydrogen applications. Thank you so much for your time, and thank you so much for the opportunity to present. Any and all questions are welcome.